No, let me explain. I passed out a quiz. Now, my Tuesday, Thursday class did not get a take-home quiz like you did. So when they came in on Thursday, this is the quiz basically, well, it's a little different, but this is what I expected them to do on Thursday. So had you not had a take-home quiz, I would have given this to you today, all right? I'm just giving it to you just as an FYI. This is what I expected them to be able to do. So I would have expected you to be able to do this today, all right? I gave them 8 minutes to do this, so. It's just for your own, information, okay?
Take up the quiz or anything?
Yes, and I will collect your take-home quiz. And what I told them was that the problem that I gave them here was not a hard problem. That this was a very easy problem because it was a time thing, you know. So I expected that they could do the slope of a tangent line. I asked them just for the slope, not the equation of the line. So I didn't want them to get any false ideas that this is how easy the test would be. Like it's just going to be a bunch of polynomial functions. It's the concept, yes. Yeah, and I didn't give them the formulas, right, for the slope of the tangent line. A lot of them couldn't remember the formula, you know, limit, all that. They couldn't remember it for the quiz. So your test is this Wednesday in 2 days, and that's just the way things have fallen for you, unfortunately. Because we had that holiday, your exam's going to land on a Wednesday instead of a Monday, and that's just the way it is. And the material we covered today will be on the exam. So you're kind of, I think I warned you about this a little bit last week, all right? But it is what it is. So we need to get started. Any questions?
Yeah, can you... What?
Okay, okay, so the last class we did not quite finish the lecture notes, so that's where I'm going to start today. What we were doing last time is we were trying to find the slope of tangent lines, right? And from that we could come up with the equation of a tangent line. And because this is used so much, we have a special name for this, all right? Finding the slope of the tangent line of a function at a point A. So like if I give you A is 2 or A is 5, right? That point that we call A, the slope of the tangent line there is called the derivative of f at A. It's called the derivative. And if you ask anyone who's taken Cal 1, you know, what is Cal 1 about? They're going to tell you it's about the derivative. Okay, it's about this process. And remember that there were two definitions, and we're going to use a new notation now. Okay, this is a new notation. Instead of writing slope of tangent line or writing out in words, hey, find the slope of the tangent line, we're going to write just f with this little, what is that, apostrophe? It's like an apostrophe a, which the way you say it is the derivative of f at a, or f prime of a. So anytime you see that notation, it means you need to apply this limit, or you can do the other formula. And remember that these limits, a limit does not have to exist, right? Limits, that happen sometimes. We got DNE. Now it hasn't happened yet, right? It hasn't happened yet when we were trying to find slopes of tangent lines, but it could. So provided that the limit exists, then the function, the derivative at A is just this limit. And there's two other ideas we need to walk away with in this section. Does that answer the question of what is f prime of A? It's just the slope of the tangent line of the function at A. It's that slope, right? That's the derivative at A. That's f prime of A. All right?
So it's just the slope, not the equation?
It's just the slope, yep.
So what if they only give us an equation and then tell us to find the slope of the tangent line? It's like, without a point, you can't do it, can you?
Well, yeah, that's a good question. We're going to actually address that today. That's a good question. All right, so what we have established geometrically is this idea that if we have x and then here's some function of x and we have some curve, that if we pick some point A and go up onto the curve, we should be able to find the slope of this tangent line, right? right there. The slope of that, m, is the same as this f prime of a. It's that limit, right? That's what it is. This slope represents what we call the instantaneous, I don't have a ruler in here. Is there not a big ruler in here? Oh, there it is. I see it. This right here, this value, this m, is the instantaneous rate of change of the function. Remember, the whole idea of a slope of a tangent line is a rise over a run. It's a rate of change. And the slope of the line at a single point is the rate of change at an instant in time. Because you don't have 2 points anymore, right? It's the limit as 2 points become 1 point. And so we can extend this into any field. Chemistry, physics, biology, does not matter. Economics. If you have a function, this slope represents instantaneous rate of change. So I'm going to give you a couple of examples of how you could see this in another field. And the first one is this idea of instantaneous velocity. And I believe this is how I motivated the whole idea when we started talking about these tangent lines, is this problem of getting, what's the speed of an object at an instant? So if I have a graph, but my x-axis is now time, let's just say for the sake of right now, we'll say it's measured in hours. And the y-axis is distance, and let's just say for now it's in miles. Then if we have some function that's telling us where something is at every point in time, right? So this tells you, give me a point in time, I'll tell you how far I've gone, right? Then if I look at the slope of the tangent line here, this gives me the instantaneous rate of change, right? Instantaneous rate of change. But rate of change in what? Well, remember, rise over run. What is our rise measured in here? In this particular problem? Our miles, right? Miles, and then that would be on top. Miles over run is measured in hours. So the slope of this tangent line would give us an instantaneous speed, right? Velocity. It would be distance over time, miles per hour. Understand? But that's just if we have distance versus time. If you go into a different class, let's say you're taking, I'll leave this in, let's change this time to seconds, right? And let's change this to temperature. And let's say that's in degrees Fahrenheit. Then your graph, you could be measuring the temperature of something every second, right? And then if you find the slope of the tangent line, this would give you your instantaneous rate of change in temperature with respect to time. So this would be like degrees Fahrenheit per second instead of miles per hour, right? Degrees Fahrenheit per second. We could change this to money, okay? Dollars. We could change this to years, okay? Then you could graph your company's profit or revenue, whatever, and you could have instantaneous rates of change within that model. Understand? So it's a very generic idea. The important thing is that the slope of the tangent line represents instantaneous rates of change between two variables. Or one variable depends on the other, but got it? Okay. And I believe that's it for this section. So we're going to start the next section. All right, I think I'll motivate this idea by starting with the problem. Let's do this quiz problem, okay? We'll make this quick and easy. All right. Let's say we're given f of x equals x squared minus 3x. We are starting 2.2 right now, all right? Just so you're clear. The test says to find the slope of the tangent line to the curve at the point 2, -2. Now, using the notation that we just established just a second ago, this is really asking us to find f prime of a, right? But what's a here for us? 2, right? A is always the x-coordinate of the point, not the y-coordinate. I saw some of my students in my other class picking the y-coordinate and putting it in here. It's the x-coordinate goes in there. And then at this point, we use the definition of this, which is one of 2 limits, right? You get to choose. Now I am going to use the h limit. Limit h goes to 0, because 2.2, we will be using the h goes to 0 exclusively. All right? So if you married yourself to the x goes to a formula, I hinted to it. You should be able to do both, okay? But this h goes to 0 is the one that we're going to highlight in this section. All right. So limit h goes to 0 of, what's the formula? F of a plus h minus f of a all over h. And this is limit as h goes to 0 of f of 2 plus h minus f of 2 all over h, right? And then we plug in. So this should be equal to the limit as h goes to 0 of f of 2 plus h, means I'm going to replace the x in the function with 2 plus h. So I'm going to have 2 plus h squared minus 3 times 2 plus h. And that finishes off the top left corner, right? Then minus f of 2, but what's f of 2?
Negative 2.
Negative 2, we knew that already. So we're going to be subtracting a negative. It'll be positive. I'm going to go ahead and write minus negative just so, since I'm going to have to do some work anyway, I'm going to just write it like that. We good? Okay. And then from here, it's just some algebra. So I'm going to expand the top left. That's 4 plus 4h plus h squared. That's the top left corner right here. You could do that, right? Distribute the negative 3 through, negative 6 minus 3h plus 2, all of this over h. And what should happen?
4 negative 6 and 2 will cancel out.
We should get a bunch of stuff that cancels. Everything that's left on top should have h in it, hopefully, right? So
H plus h squared.
yeah, I think that's it right there, right? Okay. We do have some like terms. We have 4h and minus 3h. That's just a single h plus h squared over h.
H will take out and equal to 1 plus h.
Good. We will factor an h out of the numerator and then cancel. I say cancel. You can say reduce there. Now let h go to 0, right? And you get 1.
And plug it into the formula.
Well, in the quiz, it just asks you for the slope of the tangent line.
That's it.
That's it. That would be the answer.
Could we have used, sorry.
Yes.
Could we have used the first method?
Yes, but just hang tight for what I'm about to do, all right? And tell me, because it's really hard for me with 2 classes, all right? It's really hard with 2 classes for me to remember exactly if I told you this or if it was the other class. I apologize. Right now, if I asked you to now go and do the same problem at 1, negative 2, you could do that, right? You'd run through this whole thing. What if I asked you to do it at 0, 0? You could do that? So last time we talked, did I list out a bunch of different ones and say there's an easier, more efficient way? No? Okay, good. I didn't think I did. So look, we just did this one, right? But if I came in here and asked you to do this, you'd have to set the whole thing up again, right? And run through the limit again. And then you would have to come and do this, set the whole problem up again, and run through the limit again, right? Yes? Yeah. And so let's say I listed like 20 different points, and I wanted you to find the slope of the tangent line at all 20 points. You would not want to have to do this 20 times, would you? You would not. So what we would do instead is say, look, maybe there's a more efficient way where I can do something and get a formula that will give me this slope where I only have to do the limit one time. So just imagine this. Instead of telling you exactly what value to go to, right? I'm going to just call this A x. Okay? It's x, whatever the heck x is. And then the y coordinate is the function's value at x, whatever that is. It depends on x, doesn't it? Like if this is 2, then that's -2. But this is 1, this is -2 also. And if this is 0, it's 0. So this right here depends on the original function. What I'd like to do is see if we can actually get an answer right now if we try and do the derivative at x. Understand? We're doing a general value for a instead of a fixed a. Do y'all understand that? Okay. So let's just write down the definition. And keep in mind, this is the slope of the tangent line at x, right? That's what this is. The slope of the tangent line at x is f prime of x. And for us, that would be the limit as h goes to 0 of f of, it was a plus h, right? But a is what? X. So x plus h minus, it's supposed to be f of a, right? But a is x, so f of x all over h. Now, let's plug in. If I plug x plus h into the original function, right, which is this right here, I'm going to replace that x and that x with x plus h. So I would have x plus h squared minus 3 times parentheses x plus h. Right, that would be the top left. What do I still need to do? Subtract f of x. Well, what's f of x? Everything, right? So parentheses, because I'm going to subtract the entire function, x squared minus 3x, all of this over h. And now let's do the algebra. This is the limit as h goes to 0. If you expand that, you get x squared plus 2xh plus h squared. That's this, right? Distribute your -3 through. Distribute this negative through. Just be careful with your signs there. And then divide all that by h. And again, the same thing should happen. We should get things to cancel with the exception of things that perhaps have h in them. So let's see. I've got a 3x. I see that one right away. I see x squareds go away. Everything else has an h, doesn't it? Everything else has an h in it. I have x's too, but I should have x's because I never told you, right? I never nailed down what the value was. I just told you it's x. So now we're here. Limit h goes to 0 of 2xh plus h squared minus 3h all over h. And what can I do now? Pull an h out of the top, factor it out. I forgot to put h goes to 0 there. Pulled my h, 2x plus h minus 3 all over h. These h's will reduce out. And now look at your expression right there. You see that? 2x plus h minus 3. If we now let h go to 0, not x, right? H. Let h go to 0. This goes away, doesn't it? And what are you left with?
2x minus 3.
2x minus 3. 2x minus 3. This is the slope of the tangent line at x. It's a formula for it. So let's go back and look at the problem that I gave you a second ago. When we were at the point 2, -2, okay, and I asked you for the slope of the tangent line, what was x? What was x here? Yes, it was 2, wasn't it? So this right here is our x. So the slope of the tangent line, right, at 2 would be equal to f prime of 2, which is, according to this formula, 2 times the x value minus 3. So this should be 2 times the x value minus 3, but the x value is 2. So I'm just plugging 2 into this function, and I'm getting 1, which matches exactly the answer we just got. The power of this, though, is that now if you want me to do this one, I don't have to do the limit again. All I do is I take, what? If I want to do this point 1, negative 2, right? At the point 1, negative 2, what's the slope of the tangent line at 1? Well, it's the derivative at 1, right? The derivative at 1, which means just plug 1 into the formula I just erased, sorry. I'll put it up here. This is what we said earlier, right? This was what all that work got us. We said, what is it? 3, thank you. All right, that's what we worked for, right? We got that answer. Now if we just plug 1 in here, what do we get? All right, 2 times 1 minus 3, we get? Negative 1, right? So on the slope of tangent line there is negative 1.
So then we can just keep on plugging.
And now you can just, people can give you values and you're off to the races. You can get as many derivatives as you want, as many slopes as you want. And you only had to do the limit one time. Yes?
For when we when it asks for the slope, do you want us to put n equals 1 or just?
No, as long as you start out in the beginning and just say equals, 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 you know?
So in other words, the prime of 1 or whatever, just asking like what's the slope at 1?
Yes, so this means to us that if I were to graph the original function, if I were to go to the x value of 1, what I can tell you, well, we know the point is negative 2, right? So I know I'd be like down here. I know that the slope of the tangent line there is negative 1. So I know the slope, negative 1's like this, right? I'd have to draw the curve to convince you. If I go to 2, right, at 2, right, at 2, what was our answer? 1. And at the point 2, we're at negative 2, so we're a little, oh, we're at the same value, aren't we? We're over here. But the slope there is what, 1? So it's done this, and then it's actually come back, so we probably have the vertex in there somewhere. Okay, y'all understand? Okay. So today is about, look, before when we wanted slope of tangent lines, we always did it for one single value, a is a number. But that's not as efficient as doing it in general and then being able to get the slope of tangent lines for any points. Do you agree that that's more efficient? Yeah. It's harder algebra usually, but the payoff is that now you have a general answer. Okay? Pardon me?
You couldn't have showed us this first?
Well, we could have. We could have. Yes. Yeah. But we want to start at a point, you know? And let me explain to you why, real quick, the other formula won't work. This was the formula, the other formula, right? Right? This was the other formula? The problem with this is the derivative at a, all right? But I said to get a general answer, we want to replace x with what? Replace x with a. So if I come in here into this formula and I replace x with a, your formula completely falls apart. A with x, sorry, a with x, right? If I replace that, then basically you get 0 over 0, and you're going to plug the same function in here as here, and x, it's always going to just be 0 over 0. There's no algebra you can do. It does not work. So this version does not work. This version of the definition doesn't work. Okay, let me bring the notes up.
So do we divorce the first one and then remarry?
Yes, you will. You can now officially marry the limit h goes to 0. You were just kind of, you know, experimenting a little bit, and now you've decided this is probably the one for you. All right. All right. So this just summarizes what I said. Up to now, we've been doing it at a single value, a. We're going to let that x now, right? We're going to let that a become x, and we have this new definition right here, right? That's it. And there's nothing new there.
After that, do we just automatically do it as f of x plus h?
It depends on the problem. You know, if the problem is asking you, like on the test you're about to have, if it says find the slope of the tangent line at, and they give you a specific point, you can stick to what we've been doing. Yeah. But if they don't give you a specific point and they just say, hey, find the derivative of f at x, then you have to do what I just said.
So now what if they put f prime of a, but they don't give you a point or anything? Is it asking the same thing?
It's asking the same thing, yes. You'll just leave your x as a.
Okay.
Yeah. Let me go a little more into this and all right, so I think what I want to do is go back to the problem we just did. All right, so we just had here a function f of x. It was x squared minus 3x, right? We just determined that the derivative, right, f prime of x was 2x minus 3. That's what we determined, right? We did some work and we've got that. What I want you to realize is that these are both functions, aren't they? I mean, the original function is a quadratic, and you could graph it, couldn't you? Yes? And this function is a linear function, and you could graph that, couldn't you? What I'd like to do is I'd like to graph those together on the same axes. You're going to have to put your phone away, sir. You're going to get yourself 10 points off the next test. I'm going to graph these together. So the first one is x squared minus 3x. And the other one was 2x minus 3, right? Wrong way. All right, so let's take a look at this. What was the slope of the tangent line? What was the first one we did? The one on the quiz gave us a specific point. It was what? -2. At 2, 2, -2. So when I went out to 2, went out to -2, right here at this point, we said the slope of the tangent line was what? 1. So what I'm going to do is I'm going to look at this function over here. Look at its derivative as a function, right? Look at it. 2x minus 3 is a line. Here it is, the blue line. If I go out to 2, where am I? Up here at 1, right? Do you understand that the height of that point corresponds to the slope of that tangent line? Do you see that visually? Yes? Okay. What about at this point right here? What's the slope of the tangent line at that bottom point? 0. Do you see that that corresponds to the x-intercept of this blue line? Because at that point right there, the y value is what? 0. If the y value is 0 on the derivative function, that means the slope of the tangent line on the original function is 0. Are you capturing that? It's a lot of language here. All right, so what I'm going to do is I'm going to start moving along this red curve with my ruler. And I want you to tell me about the slope of the tangent line. Here, is that positive or negative? Negative. Negative big number, negative small number.
Small number. Big number.
Remember we said small means close to 0. So that should be a very large negative number. All right, so imagine that point right there. So how would I confirm that? Go to the blue function. What is the blue function at this value? Hey, a very large negative number, isn't it?
Probably 5%.
And as I move to the right, what is happening to that tangent line, the slope? Is it still negative? Yes, but it's getting closer to 0, right? It's getting smaller. So notice what's happening as I move along the blue curve to the right. I'm still negative, right? Still negative, but I'm getting smaller until I get to here, right? And when I get here, look, it's 0, and that matches up with the slope of that tangent line. Once I get past this, right, what happens? The slope starts to turn positive, and as I go further to the right, it gets to be a larger positive number. Do you get that? So with every graph, with every function f, we should have a graph, we could theoretically put down a graph of its derivative, and that connection would always be there. Understand?
So the correlations are the slopes?
The slope of the red one corresponds to the y value of the blue one, the height of the blue one, at that x value. So you go out and pick an x, go up to your function, find the slope. If you go to the same x value on that blue one, that's the steepness of that slope, the height of that point. Now what I'm going to do is I'm going to give you another example. I'm going to draw a function for us, all right? And then I'm going to ask us to draw the derivative. All right, so here's a graph. And I'll do this one. Let's say that each of those little tick marks is 1 unit. So I'm going to draw for you now a function, f. Here it is. Trying to figure out where I want to land. Okay. There's a function f. See it? That's f. I would like for you to draw, and we'll do it right below it, I'd like for you to draw its derivative. What does f prime's graph look like? Well, what we're going to do is we're just going to first start over here somewhere. We're going to pick an arbitrary point. So let's just pick an arbitrary point. How about at -3? If I go up, what does the slope of the tangent line over there appear to be? Negative, right? Can you tell me like any more detail? Like, do you know the slope? Wouldn't it be the slope the same, since it's a straight line, isn't it the slope of that line? Yes? And can you tell me the rise over run of this? Down 1 over 1, down. So it looks like -1, right? So at this x value of -3, the derivative should be what? What's the value of the derivative at -3? It's the slope of that tangent line, which you said was -1. I'll just put it down here. Agreed?
So it seems like you can use slope and derivative interchangeably.
Yes.
So it's really just
It is the same thing. The slope of the tangent line is the derivative of the function, well, at that point. So what about if I pick this point right here? What's the slope of tangent line there?
the same.
Same, -1. What about here?
The same.
Same. Any point, right, on this line segment, anything on here, the slope would be -1. So if I go to any of these x values down here, all the way until I get to here, here's -1, the slope should be -1, shouldn't it? So I can say, fill this in with a bunch of -1s, which really just creates a solid line, doesn't it? And I can actually take this arrow out this way because it looks like it just stays doing that to the left. That's what the derivative looks like. Then, when I get to -1, something really crazy happens. My slope goes from -1, immediately switches to what? +1. Right at that point. So at -1, it's going to switch up to +1. Like, right, if I'm here or here, any of these points, the slope is 1. So here's 1 unit high. It'll be all those. See how those correspond? All these dots correspond to the slopes of all those dots, at all those dots. So I could connect these together. Boy, that's supposed to be straight. And then what about over here, when I'm back on this side on this piece?
Going back down?
I'm back to -1 again, right? So I'm going to be back down here at -1, well, a bunch of dots, and I connect them, and it goes like this. That is what the derivative looks like. The only part that we still need to figure out is what's happening at -1 and what's happening at 1. Does not exist. Okay, we have open holes here, like this. And do you remember that I said that the derivative, right, we define the derivative as a limit. Sometimes that limit doesn't exist. This is an example of a function where its derivative doesn't exist. Where does the derivative not exist for this function? F prime of -1 and F prime of 1, both of these do not exist. The derivative does not exist. And in the lecture video for today, for 2.2, which you were supposed to have watched, and that's also the second question on your quiz, is it says a function can fail to be differentiable. It can fail. There are three types of problems that can cause our function to fail to be differentiable. And I asked you to name one of them. This is one example of where a function would fail to be differentiable. Anywhere where we have a corner, or what we also refer to as a cusp. A cusp would look like this. If I drew a function that did this, that would be a cusp. If you have a corner or a cusp, then at that point, just at that point though, your function would fail to be differentiable. Everywhere else, it's differentiable. You have a derivative. You have a slope of a tangent line. It's just at that corner you don't have a slope of a tangent line. You with me? All right, there are two other places where a function could fail to be differentiable. What are they? Anywhere your graph has a jump. Okay? So if you have a function f that breaks like that, if this is f, and let's say this is happening here at 1, then what you can tell me is f prime of 1 does not exist. All right? Why? Because the original function f has a break, has a jump. So at corners and cusps, you fail to be differentiable. At jumps, you fail to be differentiable. And there's one last one. And this is what we call a vertical tangent. So if you ever see a function that does this, something like that, what happens here is that as you look at the slope of the tangent line, what's happening here? It's trying to become vertical. And vertical lines don't have a slope. The slope of a vertical line is undefined. Therefore, wherever that point is, again, we'll call it 1. Let's just say that that was 1 unit out, all right? We would say here f prime of 1 does not exist. Those are the three places it can happen. All right? I'm going to draw another function. I want us to be able to draw the derivative. You ready? And on this one, I think I'm going to give you a minute to think through it yourself. This is f. I want you to sketch below it f prime. I'm going to give everyone about a minute and a half to see how much you can come up with this, how much of this you can come up with, and then I'm going to talk through it. Doesn't have to be perfect. If you're completely stuck, don't worry about it, all right? There kind of is. Does anybody, by show of hands, feel like they have something? Yeah? Okay, maybe. Okay, I think that's enough time for you to get some idea. All right, so if I was looking at this, I would go and try and pick out the parts of the graph that I know for sure something about the derivative, about the slope tangent line. And that's probably here, here, and here. Would you agree with me that at those 3 points, the slope of the tangent line is 0? Yes? If I drew a little tangent line here, the slope would be 0, here the slope would be 0, and here the slope would be 0. So if I go here, here's my x-coordinate. If I just come straight down, here's my x-coordinate. The value of the derivative there should be 0. The value of the derivative here at the origin should also be 0. And the value of the derivative about right here should also be 0. Do you all understand that? Yeah? Then what I would do is I would maybe just pick some arbitrary point to the left of this one and just talk about the slope of the tangent line here. It's what? Positive, right? And as I move further to the left, it's going to still be positive, but it's going to get steeper, which means bigger positive. And as I keep moving to the left, I'm going to get steeper and steeper and steeper, aren't I? So as I start from this point and move this way, my derivatives should be positive numbers that get bigger. So it should look like, come on, maybe like this. These are positive values, right? They're positive, and they're, as I move to the left, they're getting bigger positive, bigger positive, bigger. How about right here? If I pick a point to the right of that point, it's going to be negative. And then as I keep moving to the right, it's going to get a little bit steeper, right? So it starts out pretty shallow, and then it kind of, like right around here, which is about right there, it kind of gets to a maximum steepness, right? And then it starts to turn back. It's still negative, but starts to get shallow again. So I've got to get back to 0, right? So start out at 0, you're negative, you start getting bigger negative, but then you start getting smaller, back to 0 negative. So between here and here, I should be negative, getting bigger negative, which means going down further, and then coming back up to 0. Do y'all see that? This is one of those things where it's a light bulb. Like when you see it, it's fine, like, oh, okay, I see it. Until that happens, it can look like there's some weird voodoo stuff happening here, all right? What happens once I go to the right of this point? Positive, right? Small positive, until I get to about here, and then it starts going back to smaller positive again, right? So I should go positive, small positives. I get to some maximum positive value, start going back to 0. And then once I get past that point, negative, and it gets bigger, negative, bigger, 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 bigger. So it should look something like this. Got it? Yes?
Yeah, why is the left side all negative?
Where? Left side of this?
Yeah, why are they negative? I mean, why were they positive?
Pick a point and draw me a tangent line. The slope of that tangent line is positive. The slope of the tangent line. Remember, tangent lines, just lines in general, this line has a slope of 0. This is a positive slope. That's always positive, right? And then the other way is negative slopes. So when I'm over here, this is a positive value, right? A positive slope. So the derivative should be positive there. Okay?
Pretty much going left to right is pretty much going positive.
It kind of looks like a reflection.
Yeah, you have to be careful with that. Trust me, if there was an easy way for me to just say, oh, take that, flip that, just mirror that, I would tell you. But you have to analyze it. You have to understand what's going on.
So essentially on the bottom when we're just drawing the slope.
You're drawing the slope, and we're not even looking to see like precise values. Notice I didn't try and like say the slope of that was exactly 8 and went over here and went up 8. It's just that it's positive and getting more positive.
What would the notation for that be?
This right here is f prime. This is f prime. This is f. This is the original function. This is what its derivative looks like. Question?
Oh, when I was looking at it, or like from the last one you did, how it had the quadratic to a straight line, like, would it be safe to assume that the derivative is going to be a power less?
Well, that's exactly what I was going to talk about next. Okay, so if we go back to the problem that we started with, which was this one, x squared minus 3x, and we actually were able to compute its derivative to be 2x minus 3, right? If I were to graph these two, the first one would be a parabola that opens up, so it would have looked like this. And then if I were to graph its derivative, which I did, I did this for us, right? It went like this. I had a quadratic as the original function, and its derivative graphed was linear, which is 1 power less than a quadratic, right? It does turn out that if your functions are polynomials, and this only works for polynomials, that whatever your function is, the derivative of it will be 1 power less. So this, you could argue, is probably a 4th degree polynomial. Remember 4th degrees, even degreed polynomials from college algebra open like this on the ends or like that on the ends. That's what even degree polynomials do. Odd degree polynomials do this or this, right? So you could argue, yeah, that's probably a 4th degree polynomial, and look, its derivative doesn't do that, it does this. So this is probably an odd power, so it's probably q. It's not going to be higher, but it does turn out to be that exactly. But we will get that after the test. We'll talk about that. All right, y'all with me? All right, we need to do a couple of practice problems. This is it for the graphs, all right? Guaranteed you will have one of those on the test, all right? There's a section in the beginning of this homework where what they do is they give you graphs and they ask you to sketch the derivative, all right? And then there's another section where they give you a bunch of graphs of f and a bunch of graphs of f prime and its match. Which graph goes with its derivative? And that's a good practice, all right? What I want to do now is look at the algebra that we're going to be playing with here with this. There's really nothing new in terms of like we're still going to be doing limits, except now we're not plugging in a value for a. So let's try this one. I'm going to give you f of x is equal to x cubed minus 7x squared plus 1. Find f prime of x. So this is really telling me, hey, look, I have a function. If I graphed it, I could look at its derivative at every point, the slope of the tangent line, and I could tell you what it is. But to do it efficiently, I'm going to actually find a function that will spit out those answers for me, right? Just like we had the 2x minus 3 a second ago. We're going to go find what the derivative for this function looks like. So I have to write down the definition. This is a limit. H is going to 0. It's f of x plus h minus f of x all over h, which is limit. H goes to 0. All right, we get to plug x plus h into that, right? That's just me plugging x plus h into the function. Minus, what's being subtracted? F of x. So the entire function rewritten again. All of this over h. And we have the pleasure of expanding this. X cubed. We talked about Pascal's triangle last time, didn't we? But I'm just going to assume that you could do this on your own, all right? Given enough time, you could get to this, right? I mean, you could, right? If I gave you enough time, you could multiply that out. Okay. And then right here, we have to square this, don't we?
Yep.
When we square that, we would get x squared plus 2xh plus h squared. But then we have to pass a -7 through it.
Yep.
So it would become negative 7x squared minus 14xh plus, oh no, minus 7h squared.
Then minus x cubed.
One more thing, hold on.
Sorry.
Plus 1, don't forget that 1 there, right? Plus 1. Then pass the negative through here. Minus x cubed plus 7x squared minus 1. All of it over h. And if there's any justice in the world, which there's not, then everything's going to go away except for things with h's, hopefully. All right, does it happen? Let's see, x cubed. Hey, plus 1 minus 1, got that. 7x squared's gone. That's it. Right? That's it? All right, well, that's life. We just have to deal with it, all right? So this equals the limit as h goes to 0 of 3x squared h. I'm happy to see an h, right? Plus 3xh squared, really happy to see an h, plus h cubed, minus 14xh, plus, or minus, sorry, 7h squared. Is that it? Get everything there? All over h. Factor an h out of the top. Notice I have not forgotten to write my limit. Every single time I write limit. All right. We good? Yeah. Cancel your h out. And now the remaining expression, you let h go to 0. Everywhere you see an h, that term is going to vanish, right? It's going to go away. So this is going to go away. This is going to go away. This is, oh, the whole thing is going to go away. And the only thing left is 3x squared minus 14x. And we are done. This is the derivative. I'm going to put it over here. This is the derivative of our function. If I were to graph these, the values of this function should correspond to the slopes of the tangent lines of the other function. That should be the correlation, right? What do y'all think?
You should let us use the Pascal's triangle in our test.
You have Pascal's triangle. It's in your head, right?
No.
Ones, 1, 2. No.
Can't bring that one.
Nope. You could use the formula sheets.
Go.
You can use the formula sheets.
We can print them out, right?
Yes, you need to print them out. I'm not going to provide them.
Oh, yeah.
Yeah, you need to print those out. The formula sheets on Canvas can be printed out. I think there's 6 pages or something like that.
Yeah.
You can have those on the test, but nothing else. So, and you can't add your own formula. Like, hey, yeah, you know what? I think I need that limit formula. Yeah. So you need to remember like limit h goes to 0. You need to remember all that. All right. Now I want to point something out here. I'm not going to graph these. Okay. I could do that. That'd take too much time. I want to point something out. I know there are some of you who have taken calculus before, either in high school or this is your second time coming through this. And those people who have seen it know that there's a shortcut, right, to get from here to here that doesn't have a limit in it, that there's no limit you ever have to compute. It's a very nice shortcut. And I'm going to show it to you right now, but we're not ready for it yet. We're going to do that after the test. So here's the shortcut. You see the original function. What you're going to do is look at the first term. And you're going to notice that this is x to the power 3. You're going to bring the 3 out front, and you're going to subtract 1 from that power. Okay? So bring the 3 out front and subtract 1 from the power, and what would you get? 3x squared. Okay? Here, I want you to bring this 2 out and multiply it times the negative 7, and what would you get? Negative 14. I want you to reduce the power on that by 1. And you get what? Negative 14x. Here, I want you to notice that that's really x to the 0 power, because x to the 0 would be a 1, right? So there's really like a hidden x to the 0 there. Bring the power out. 0, it's gone, right? And that's it. We're done. That is a shortcut. It's called the power rule. You will be given that rule. That'll start in 2.3. That sound good?
So we don't recommend using that all the time?
No, you have to, we're going to act like I didn't show you this, okay? But you can check your answer that way, right? You could check your answer that way.
Check our answer with a calculator.
So,
Saying, like, we can be friends after you break up with
yeah, we're going to still be friends. So now look, I know you're going to get upset about that, all right? I know that frustrates a lot of Calculus 1 students is, okay, why do we do all this limit stuff and then we get to this point where we give you all these shortcuts? And part of the answer is, look, what separates this class from business calculus, in business calculus, they do calculus, but they don't mess with the limit, okay? They see it a little bit, they say, hey, this is the idea, and then they go straight to the shortcuts. And they also limit themselves to just polynomial functions and some rational functions. They don't ever touch trig functions, they don't touch exponential, logarithmic functions. Well, no, they do. But they stay in a very narrow field of functions, and they get all the shortcuts. Here, as calculus students, we must suffer through the limit for a while, then we get the shortcuts, all right? And you're all happy because you get these shortcuts and the limit goes away. And then we say to you, okay, you like the shortcuts, that's fine. Now we're going to crank up the functions. So instead of sticking with just polynomials and rational functions, we'll give you something like, I don't know, the function f of x equals, I'm just leading you, okay? Sine of x squared plus 1 over x cubed minus 1. Like, there you go, that's a function. I'm sure we could graph that. And if we graphed it, maybe you could tell me, about its slopes of tangent, the slope of its tangent lines. So what would the derivative of this be, right? And so the rules that you have there are very nice, but to do this, you're going to need more than just that rule. There's going to be actually a few rules that we have. We have the power rule, which is this rule. We have the product rule, which you'll see. We have the quotient rule. And then we have the almighty chain rule, all right? Those are the big rules. Once you have those rules, you can theoretically take the derivative of any function, all right? So you have to be careful what you wish for, because you might just get it. You might just get these shortcuts and then realize, crap, now I have to do a lot harder stuff. But that's the reality of it, okay? I mean, I've never wanted to sugarcoat anything for you or make it look better than it is. It's exciting. We'll be able to do a lot of functional analysis once we have all these rules. All right. One more thing I want to show you. We'll do another example, but I always love to show students this. So I want you to just take a step back. Take a step back to college algebra. This is a quadratic function, right? A general quadratic function. So, hey, all quadratics look like this. They did tell you that A, B, and C were just numbers, right? So if somebody gave me A, B, and C, then I'd be able to graph that parabola. They also told me that A could not be 0, right? If A was 0, then that would go away and it would no longer be quadratic. So that was another condition I had to have. Other than that, that's a quadratic function, right?